Next thing we want to talk in here is about the design of the process piping. This is not a design course, and we're not going to go that detailed on stress analysis to calculate the support and things like that, or the loadings that happens on process piping like a wind, earthquake, stuff like that. But all the certification program, you go to the API 570 or AWS, endorsement exam, all of them actually in any way expecting you to be able to calculate the wall thickness of the your process piping by design pressure, actually with the design thickness, okay, with the internal pressure. You're having an internal pressure on your pipe, so just considering the internal pressure and not the structural stuff, you should be able to calculate the wall thickness for internal pressure, which is, we name it hoop stress or circumferential stress. You're having the hoop stress, which is acting on all the 180 degree of the pipe and wants to tear down the pipe from here. And those hoop stress, to overcome to that hoop stress or circumferential stress, you need to have some wall thickness to resist against that circumferential stress or hoop stress. We're having the Barlow formula here. The Barlow formula is very simple. It calculates how is the stress causing in the wall, but they changed it to the different design formula. All of them are the same. If ever you are in the pressure vessel ASME section 8 division 1, or you are on process piping, if you are on the pipeline B31.4, B31.8, all of them using the Barlow formula for calculation the wall thickness, but they have some addition, some modification. They have different code committees, and they sit together and to see how they can get the higher thickness for safety factors. The safety factors for pressure vessel might be different from the process piping, but the way they add these safety factors, that's caused that this design formula from the one code to be different from the other one. I put in a screen, you can see the formula came on B31.3, which is addressed on 304.1.2, and it's named straight pipe under internal pressure. It means the T value you can see in here is the amount of the wall thickness you need to resist against internal pressure, or which is caused the hoop stress in here. Okay, in the formula you can see we are having several variables. We are going to discuss about these variables. The first one is the P is a design pressure. The design pressure comes through the customer or owner or his engineering agent, which is considered what is going to be maximum pressure inside of this process piping, and then determines the pressure, and we name it design pressure. And then D is outside diameter. It's not nominal pipe size. So if there's a 6-inch pipe, then it's going to be 6.625 inch. Actually, you need to go either to the API 574 to read what is the OD, or you have to go directly to the source. Source is the ASME B31.3 and see what is the outside diameter of the 6-inch pipe. And then in the denominator you can see the value of the 2, that is, and then S is the stress value. Stress value is taken from the A1 table, and it's different in the different temperatures. Before going to this stress value, I would like just to explain to you, if you're not familiar with the yield strength or tensile strength or allowable stress, and then we can provide some information here for you. The material, if I put this in a tensile machine and I pull this, normally it's a straight portion of this. If we cut a straight portion of this and put in a tensile machine, and then we pull this and a certain value, if I release the load, it's gonna return to its original dimension, but it's gonna increase in the dimension. You consider, depends on a load that I am implying on that. So If I pull this, increase and a length, which we named strain, and if I release this, this is going to return to its original dimension up to certain stress that I am putting on this. I put in a screen, you can see the stress strain curve, and you can see the point of the yield point, which is up to that point is going to be from the elastic deformation, which when I say return to its original dimension, I'm talking about the elastic deformation, because as soon as you release, in a fraction of a second, it's going to return back to its original dimension or length. But after you pass that yield point, which for this material, which is the ASTM A106 grade B, is a 35,000 psi. Okay, for this material is a regular carbon steel with a pipe that's normally used on refinery and petrochemical plants. The ASTM A106 grade B is a 35,000 psi at the room temperature. Go up to 100 degrees Fahrenheit or even a little bit more, it's going to be 35,000 psi. After the 35,000 psi, you implied on this piece of the, I said a test specimen that I cut from this, it's not going to return to its original dimension, and you are passing the yield point. A little bit more stress, you're going to get, you can see in the curve, you're going to get more strain, more increase in the length, or I can say deformation. Until at the point, I've cut a piece of this, put in the tensile machine, at the one point, that's start to necking. When it start the necking, it means that it's a tensile point or ultimate tensile strength point, and after that shortly it's going to break. Okay, then that point is a tensile strength, which for this material ASTM A106 grade B is a 60,000 psi. So you have a journey from the 0 to the 35,000 psi, which is your elastic limit, and after elastic 35,000 psi to the 60,000 psi, which is implying more stress, you're getting more strain or deformation until you get the 60,000 psi, which is your necking point, and it's ultimate strength. So what am I supposed to do? Let's back to our formula, Barlow formula, or B31.3 formula for designing our design thickness, wall thickness for internal pressure. What am I supposed to put on this S? Am I supposed to put the 35,000 psi for yield strength, or should I put the 60,000 psi tensile strength? The answer is none of them, because if I put the 35,000 psi, you can see the S has a reverse relationship with the thickness. So you put the 35,000 psi, you are putting the S stress or yield strength that it is almost a deform. You are putting the elastic to the plastic transformation point. So you don't have any safety factor. I mean, if you put 35,000 psi on that formula that I said to you, yield point, it means almost to explode this pipe under the pressure, which you're going to calculate for a wall thickness by this formula. With this formula, you're actually calculating the wall thickness. So it's very wrong things. You put 35,000 psi, which is your yield point, on this design formula. What you normally do, the code committee normally comes and consider some safety factors, and then consider very lower stress than 35,000 psi for the value that they're going to put there in formula. That normally they say allowable stress. It means we're not going to let this go up to the yield point. We're going to put the stress in here way below the yield strength, and then we're going to get obviously thicker piping. You can see it in the formula. They have an opposite direction. So if you put the higher stress value, you're going to get the thinner pipe. If you put the higher, if you put the higher value, sorry, if you put the higher value, you're going to get the lower, a thinner pipe. And if you put the lower value for stress value, it means higher safety factor, actually you're going to get the thicker pipe. So all of them come with the cost. You know, there's lots of discussion how they, you know, manage and determine what's going to be these allowable stresses on the formula. And then normally is be reviewed in any, you know, when it's the time to revise the code. So by the way, we are having the table for that. The table is named A1 table, that you can go over there and to see what's the allowable stress that you're going to take and put on your design formula. For example, I think for this material, A106 grade B should be almost 20,000 psi. So I'm not sure, but I think it's going to be 20,000 psi. So what was your yield point? It was 35,000 psi. So it's like a 20,000 psi, probably. Then it's you are having you know, lots of a difference between the your allowable stress to the yield point, and that's why allowable stress. And also it's different and a different temperature. That depends on your design temperature. You're going to read that allowable stress at the design temperature. Like I said, this is a 35,000 psi is your yield point, and 60,000 psi it's your tensile strength at the room temperature. What if I put this in a furnace and raise the temperature to the 600 degree Fahrenheit? I put it to the 100, you know, to the 1100 degree Fahrenheit, and then we put in a tensile machine. We have a tensile machine that they can make a, you know, all of these tests, yield, strength, and tensile and elongation at elevated temperature. Absolutely, you know, that's what the blacksmith does, right? They puts the material on steel on the fire and the charcoal, and then take it out and just start the hammering to deform it and shape it. So the same thing's in here. In the higher temperature, in the elevated temperature, you're not going to have the same yield strength and tensile strength, and it's going to be way lower than that. The same thing is going to happen in here. In the chemical plant, in a refinery, you are dealing with the very high temperature services. So what we're going to do is that we're going to go and read this S value, which I name it and name it is the allowable stress. You go over there and there's a table which is a combination of the material and the different temperatures. You read the allowable stress at that certain temperature, which is indicated on the problem that you're going to solve, and then put in this formula. And then you're having a E value on this design formula, which is a quality factor, and it's addressed on the A1A table for casting pipe and for A1B table for actually the regular pipe, welding pipe. I mean the pipes that is made by you know, the process which is other than casting. So those different table is used. We don't normally use the casting in the process piping. By the way, might be old pipe still existing in some refineries that are used for casting pipes. And for the sewer system, yes, but not for real process piping system. But there's a table for both of them, but we are mostly are going to use the A1B table for regular piping, which is manufactured by the process other than casting, by the rolling and drying. Either they are the seamless pipe, either they are as a electric resistance welding pipe or the fusion welded pipe. This pipe, as you can see, is a seamless pipe, so there's no seams in here. I'm not talking about the circumferential joint, I'm talking about the long seam. When in this design formula, you can see E is talking about the long seam. So if there's a seamless pipe like this A106 grade B, you're going to put the value of the 1, because A106 grade B, doesn't matter, grade A, B, C, all of the A106 grades are seamless pipe. So when the pipe is a seamless, you're going to put 1. And it's also indicated in the A1B table. But if there is a fusion weld or electric resistance weld or spiral welding, anything that is existing in the industry, you're going to go over there and read the joint quality factor from that table. And then there's a new addition in the book, added a W, which is named as the weld joint strength reduction factor, which normally applies in the high temperature services when the temperature is over 900 degrees Fahrenheit, and justifies as that the material weld normally have a lower strength in the higher temperature. Again, it depends on long seams. So normally it's going to be 1 when the pipe is a seamless, and in the about 900 degrees Fahrenheit normally is covers low alloy steel and not regular carbon steel, which is like this is A106 grade B. And then the T, which we're supposed to calculate, that is the pressure design thickness. And then you're having the P value, which is the same design pressure. We're going to put also that value on the denominator. You can see in the screen. And then you are having a Y value, which is the coefficient. There's a table for that, and it depends on the temperature. Most of the time, in the temperatures that goes high, it's a 0.4. You're having a table. You have to see and check that value from the table. I'm going to put that on the screen in a minute, but the formula you can see in here, I put in a screen now, joint quality factor. To you get a little bit familiar with this table, you can see my pipe with the A106 grade B is 1 because it's a seamless pipe, and you can see the A53 pipe, which is almost similar to the A106 but normally used in the lower temperature a little bit, and is in the type S, type E, type F. And for type S, which is a seamless, you can see it's considered 1. For type E, which is the electric resistance welded pipe, they put it 0.85. And for type F, which is the furnace butt welded pipe, they put 0.6. So this is a table over there. Whenever you want to calculate, you're going to go over there and use those table and then take the values and put them in the formula. There's another thing comes, this is a standard, but some designer or owners of the process piping owner wants to use the non-seamless pipes with the seams, and they want to increase these joint factors. Then they can make additional NDE and increase a little bit this joint factor. Like if one comes 0.8 and then they want to increase it to the 0.9, because it's gonna reduce if you are going from the 0.8 to the 0.9, or you are going from the 0.9 to the 1, actually you are reducing your wall thickness. So some designer or owner users might want to have a lower thickness pipe, but they want to spend some money on making radiography testing on the long seams, which is the comes from the manufacturing process. So they have a certain degree of the ND on them. So if the additional ND being performed, then they can get increase the joint quality factor. Here says that I put in a screen, the factor can be increased for electric fusion welded pipes, only electric fusion welded pipes, by conducting additional radiography, a spot or full as per table 302.3.4. I put it on the screen. You can see this table, and you can increase the joint quality factor by applying more NDE, but it is only cover electric fusion welded pipes, and it's not going to cover electric resistance welded pipe. And then just you get familiar with the way we're going to calculate our wall thickness. I put also A106 grade pipe, exactly this pipe that I'm having here, for allowable stress. As you can see at the room temperature, my allowable stress for this pipe is 20,000 psi. At the 200 psi is the same, 20,000 psi. But as the temperature goes high, you can see the different values. Okay, 19.9, and then 19, and then 17.9, and then 17.3. These are KSI. You have to multiply them to the 1,000 to get the value. And then 11.4, and then 8.7. You can see the allowable stress remarkably reducing as you are increasing the temperature. And it's 100% makes sense, because in the high temperature material gets softer, and then the formation is going to be more easier. Then you need more wall thickness to resist against that heat, that high temperature, right? So actually you're putting the S value, and the S value is in denominator, and that's going to affect your wall thickness. Lower value on S value, you're going to get higher wall thickness. That's why in the higher temperature surfaces you normally see high wall thickness values. And then I put also the table that I mentioned to you about the Y value. I said to you is dependent on the temperature and also the material that you are using. So for ferritic steel like this one, anything that the iron element is more than 50% is considered the ferritic steel. Normally is 0.4 when your temperature is below 900 degrees Fahrenheit. You can see the